Hello, and welcome to demola. And today we are going through 2024 OCR Chemistry Paper 2. Hopefully, going to get it out in time before your exam. No time to waste. Let's get it. Okay, so first of all, we're looking at this question. It said, all compounds have covalent bonds. What is the electrostatic attraction in a covalent bond between? So you just need to kind of know the terms. So shared pair of electrons and the nuclei of the bonded atoms. That's going to be the answer. That's a covalent bond. But just know what the others are to help you out. So this is a metallic bond, this is an ionic bond, and this is intermolecular. So just know the different ones, and that should help you out. But that's just kind of a knowledge mark. And then this one as well, in terms of reactivity of alkenes, well, what you should know is in an alkene, in that double bond, we're going to have one of them is the pi bond, and the other one is the sigma bond. And typically, the pi bond is a bit weaker, which allows your alkenes to be more reactive than your alkanes. So we'll look for the one that lines up with that, and you can see here, well, alkenes aren't polar molecules for one. The carbons have similar electronegativities. And then atoms in an alkane have a full outer shell. Alkenes have a full outer shell as well. So bonded enthalpy is higher. Yes, so sigma bond is higher than the pi bond, so we're going to go with C. And this is not true. Sigma bond is not lower than the pi bond. Okay, so I'm looking here. We've got iodalkanes and we've got silver nitrate. So you just need to know your test with aqueous silver nitrate, right? Just remember them. So they get more colored as you go in the group. So we go from white to cream to yellow. And because we're using iodine, I'll lock in D as the answer. And now for 4, you're thinking, okay, I think it's so much easier when you actually draw out the molecule. I think it's just so much easier. So what we'll do, you can see that I was an alkene. So that's that. So we've got 3 bonding pairs and no lone pairs. So that should automatically make you think trigonal planar. So we're already looking at B or C. And then for Y, what we're going to do is, okay, that's alkane. So we've got the 2 carbons there, we've got hydrogen, hydrogen. We've got 4 bonding pairs with 0 lone pairs, which automatically tetrahedral. So our answer is going to be B. Okay, so for this one, first of all, let's identify the functional groups. So we've got alkene and we've got alcohol. So I'm already thinking alcohol on the end of the chain. I can probably do the acidified potassium dichromate. So I'm thinking, okay, A and C have that. And we're also thinking for the alkene, you do the bromine water, where it discolorizes. So the answer should be C, because it's got both. Now, just know what the other ones do. This would be very, very useful to know as well. Now, calculation real quick. So what we need to first of all find is if we're working out the volume of oxygen gas at room temperature pressure, we know we're going to use the ideal gas equation, right? So I'm just thinking, okay, we need to find the number of moles of oxygen. Cool. So we're going to do the 4.3 divided by the ml, which was kindly given to us as 86. So I'm going to pop that into my calculator. And when I've popped that into my calculator, I got 0.05 moles. Cool. That's a 1 to 7 ratio, so we'll just do 0.05 times 7. And then we're going to get 0.35 moles of oxygen. And then if we're using ideal gas equation, just multiply it by 24, and that should give us our answer. So 8.4, which is D. Okay, unfortunately 7 is pretty much just like a knowledge mark, pretty much. So it's kind of you know or you don't, but the answer is A. And then for 8, you're thinking, okay, so which initiation step would occur of UV? The all the initiation steps, that would be my first check. Just make sure the all the initiation steps. And then you're thinking, okay, in this molecule, well, we've got a carbon that's surrounded with 2 fluorines and 2 chlorines. Or you need to think, okay, which is the weakest bond here? The weakest bond is between the chlorine and the carbon. That's what you need to know. So that's the one that's going to break. Cool. So when we look at it, and the reason why is because fluorine is more electronegative, and fluorine is also has a smaller atomic radius. But now, if we look, okay, which one is the chlorine bond? So we're not going to form this carbon radical. It's not going to be the fluorine radical. And when you're doing radicals, it's not going to be Cl2, which means your only viable answer is C. Okay, so in terms of secondary amides, what you need to know is that an amide is going to be, it's going to first of all have the C double bond O and then N, H, or N, whatever. That's an amide bond. Cool. So we need to look, okay, primary, secondary, or tertiary, right? So it's dependent on how many carbons the nitrogen is attached to. So you can see here, this nitrogen is attached to 1, 2, 2, 3 carbons. So this is a tertiary amide, yeah? And you're kind of working like that. B, you can see how the carbon with the carbonyl group is not actually attached to nitrogen, so this isn't an amide. You can see C, this nitrogen is actually 1, 2. So this is actually a secondary amide. And this one, you can see it's only attached to 1, so it's a primary amide. So our answer is C. Now, okay, let's look at this question. So we've got a gas reacted with hydrochloric acid to form this random compound, and we want its concentration in mole per dm cubed. So we need to do some calculations. What we're going to have to do is really find the limiting reactant, and that will tell us the number of moles of that solution we have. So let's quickly do that. So 1.35 divided by 45 is going to give us 0.03. And then we also have to do, okay, if we're getting moles, we need to do concentration times volume. Remember going to the MQ, so 2 multiplied by 0.02 gets you 0.04. This is the lower one, which means that that's the limiting reactant. So we're going to use 0.03 moles, divide it by the volume again, 0.02, and we're going to get 1.5, which means that we're going to use C as our answer. Okay, so now we're using IR spec. So I've got my data sheet in front of me. That's what you need to get. And we need to look at what are the major peaks. So this one is kind of like your interference that you always get. We don't really worry about it. Let's look at the peaks we have here. So this peak up here, we have it like around 3,400-ish. And the only peak that really gets that high is either OH or NH. So that's the only thing that that one could be specifically. Okay. Let's look. We've got this really broad one here as well, and it's spanning from like maybe like that's 2,600 to like the low 3,000s. So I'm thinking literally that broad peak is only really ever going to be COOH. And then we also have this peak here, which is like between, I want to call it at 1,700 about. So 1,700, I'm looking at my thing, and that's literally going to be either C double bond C or C double bond O. So when you put all of that together, you're thinking, okay, realistically, what's really going on here is I've definitely got an OH over carboxylic acid because that's going to be the really broad peak. So I've got COOH, but then I also have this peak, the furthest to the left, which is definitely just an alcohol group on its own, or it's either an amine group on its own, either or. And now that means that we're going to have to probably go with D because it's got both of those groups in there. And then here, I just wanted to show you the molecules. So we've got two molecules that are joining together. And what you're looking at here, what's going to react to form your amide bonds, it's these two, right? So if we're going to form the C double bond, or we should go like this, really, then what's going to be left is the H and the chlorine. So it's going to be A, not B. Okay, so for this one, we're looking at a gas chromatogram, and we need to just see which of the statements is true. So the P of the component X shows the mass of 1 mole. No, it does not. If a question for part 2 says component Y stays in the column longer for X. So you can see here, yeah, so in terms of time, Y is no longer than X, so I can take that. And Z consists of more than half the sample. Well, let's look at the relative peak areas. 1 plus 3.5 plus 5.5 is 10. So is 5.5 greater than 10? Yes, indeed. So that's also true. So 2 and 3 are true. So we're going to go with C. So we've got another one of these questions. So we're just thinking, if I'm looking at the carbon NMR, I'm just thinking, okay, what do we actually have here? Well, I can see here we have a C double bond C and a C bond C environment. So that's going to have 2. This is a C bond O and a C bond C environment. So that also has 2. This one, it does have the benzene ring, right? I'm not going to draw it, but it has the benzene ring. But then you've got to think, this carbon, yeah, can we accept that because it's attaching to the benzene, it's not technically a C bond C? So this one's going to have 1 carbon environment, which is why we're going to go with B. And then 15, they said there's a problem with the question. So they gave everyone the mark in the exam series. So we're not going to do it. Okay, so first of all, we're going to say for this one, which hydrocarbons are unsaturated. So unsaturated means that we're looking at the presence of a carbon-to-carbon double bond, really, or just that there isn't the maximum number of hydrogens. So B doesn't have the maximum number of hydrogens. I can put that down there. C, benzene also doesn't have the maximum number of hydrogens. We're going to put it down. D has a double bond. E has this thing. I forgot what it's called, but yeah, it's got one of those. In terms of alicyclic now, we need to think, okay, well, look here, cyclic compounds, A and B. Yeah, those are the only ones that are cyclic compounds, so we're going to put A and B. Which hydrocarbons have a general formula CnH2n? We're thinking alkenes and cyclic compounds both. So A and D, alkenes and cyclic compounds of CnH2n. Systematic name for hydrocarbon C, so let's look at it. So we've got a benzene ring, Yeah, so benzene is going to be at the end. That's what we know. We need to look at our functional group. So we've got this one, an ethyl group, and we've also got two methyl groups. So now we just need to number the carbon. So I literally just start the ethyl. So again, we want to use the lowest numbers possible. So 1, 2, 3, 4. So are we happy to call it 1 ethyl 2,4 dimethyl benzene? And I can write it there. So we're calling it 1 ethyl 2,4 dimethyl benzene. Okay. Now we need to explain why hydrocarbon D is a stereoisomer. So I always like looking at this in the displayed formula. So if I start with a double bond, we've got H5C2 group, and we've got a hydrogen here. And then on this side, we've got a, sorry, my bad. I've done it the wrong way. This is H3C. Sorry about that. And this is C2H5. And this is CH3. So we need to think, okay, what are the higher priority groups? Well, we're going to go for the longest carbon skeleton in this case due to your Kahn-Ingold pre-log rules, which you need to learn. So our high priority groups are here and here. So because that is the case, that means that they're on the same side. So this is a Z isomer. So it's a Z isomer, and we're going to say that high priority groups. And then name them, very important because it's 2 marks, so name them. So CH3 and C2H5 are on the same side, and that should get you both of your marks. Yeah. Okay. So looking at this question, we're talking about alcohols and their reactions, right? Now, elimination reaction of this one, a primary alcohol, the only thing we're really going to be able to do is remove this and replace it with an alkene. So the way we do that is we use heat and an acid catalyst. So that's what you want to write. You can write H2SO4 or you can write H3PO4, but regardless, just make sure you're doing an acid catalyst, but it has to be one of those two. I think also if you do H plus, they'll allow it. Now, in terms of the organic product form, you can use any type of formula. I just prefer skeletal, really. So what I'd do is we have 1, 2, 3, 4 carbons, and then I just put the double bond here because it was on the end. Yeah, that should be enough to get you a mark. If you want to draw it out in another way, do so. I can also do the structural formula just because I know a lot of people prefer that or the displayed. But I just prefer skeletal. But that is what you're going to see. You're going to form an alkene. Cool. Now, in terms of oxidation reaction, well, this time you've got a secondary alcohol, right? Because that's attached to a carbon, that's attached to 2 carbons. Yep. So, in terms of oxidation of alcohols, you're always doing acidified potassium dichromate. So CO2O7 minus and then H plus. And now when we're doing that, because it's secondary alcohol, we're going to form a ketone. So again, we're doing 1, 2, 3, 4, and then I'm just going to pop it on here. But again, if you wanted to do it in this structural formula, you can have it as CH3, CH2, CO, CH3. And either of those would be accepted and fine. What I would say is don't do like the named formula. Like if you just said butanone, then I'm not sure you would get the mark, right? Make sure you're doing it because it said show. So skeletal, displayed, structural, either of those are fine. Okay, so regarding substitution reactions, you're always using like a sodium halide with acid. So like I'll just default to sodium chloride and H2SO4. So it's that and acid, fine. Then when we're substituting it in, just literally make sure it's going in the same place. So this one I actually might just do skeletal just because it's a lot easier. But you can see here, we're literally just replacing that OH with the chlorine. You just need to make sure it matches. So if you use sodium bromide or sodium iodide, just make sure that it matches. That's all they really want to see. Now, if we say esterification, this is a bit different. So if we have an ester forming, we need to remember that ester is alcohol plus carboxylic acid. So we're going to use a carboxylic acid, yeah? I don't like to complicate my life, so I'm going to say that we're going to use CH3COOH. We're just going to use ethanoic acid, yeah? Simplest of the lot, yeah? So just say that you're using an ester. Now, just remember as well that you're using an acid catalyst as well. Just remember that. So, in terms of the organic product, now this is where things get a bit techy. I would maybe go displayed here just because it's a bit easier to draw and you've got a bit more space. So it was thinking, okay, we need to draw the ester bond. So that's the ester bond. Yeah, cool. Now, if we just add on the rest of the molecule, we had this carbon was attached to 3 methyl groups. So we're going to have H3C, CH3, CH3. Cool. And then we just wanted to keep it simple. So we just decided, let's just do that. And that should be fine. Okay, so we're talking about synthesis of haloalkanes and reacting alkanes with halogens in the presence of UV light. So we're talking about free radical substitution. Now, so we're forming alkane with bromine to form 2-bromo-2-methyl propane. So writing the equation, we just need to do methyl propane plus bromine, basically what the question has told us, and know what's being formed. Right? So if we start with drawing methyl propane, again, like I say, I prefer skeletal formula, it's just quicker. So this is methyl propane plus bromine gets us to form, okay, it's 2-bromo-2-methyl propane. So if we do the propane, we need to do the methyl group and the bromine. And then we need to know as well, we're forming HBr. So that's knowledge that you should have beforehand. Yeah? In terms of the reaction, we've already talked about this. This is radical or free radical substitution. And then in terms of the type of bond fission, you need to know this, yeah? In terms of radical substitution, it's always homolytic fission. Most other things are heterolytic, but specifically free radical substitution, you are always going to say homolytic fission. Okay. Now, in terms of limitations of FOS, literally is what they're asking you, it's just asking you what are the limitations. You always want to say like multiple substitutions. So this is like saying that, okay, this time we only added 1 bromine, but because the reaction is kind of uncontrolled, you could add 2 or 3. And then also another thing is that addition at like different parts of the chain. So substitution at different parts of the chain. So we got 2 bromo, right? But you could easily get 1 bromo, you know, like it literally just depends. So I think, yeah, there we go. Okay, organic synthesis. So these questions can be a bit overwhelming, especially given how much you have to do. 9 marks as well. So we're going to try and smash it. Now, let's start at the top with bromoethane. Yeah. So to go from a haloalkane to an amine, we need to react excess ammonia. Cool. That's our condition. Yep. Excess ammonia. Now, in terms of what it's going to be, this is just a substitution reaction. So we're going to kind of draw the same thing that we can see with bromoethane. Sorry about that. We're going to draw the same thing that we can see with bromoethane. And then we're just going to replace that Br with an H2. Remember, with NH2. That's your amine. Now, same thing. If we want to go from an haloalkane to an alcohol, what we need to do, you would normally kind of react with sodium hydroxide. Yeah, probably some heat as well, but sodium hydroxide is going to be your reagent. Yeah, so we're going to write that in. Sodium hydroxide. I could also get away with just hydroxide ion. And again, it's a substitution reaction. So literally, copy what you got from ethane, but then look at the functional group specifically and be like, okay, it's now going to be an alcohol group. Okay. Now, to go to a nitrile group, this is where you need to now add cyanide. Yeah? So, we're going to use cyanide as a reagent. Yeah? You could add ethanol if you want, but the main thing is cyanide. And thankfully, they haven't told us to draw it out. I maybe would go like sodium cyanide, actually. Play it on the safe side. Sodium cyanide. Cool. Now, from the nitrile, this one is a bit more difficult because I think a lot of people don't know these reactions with nitriles. Yeah, so make sure you're aligning them. But in terms of going from nitrile to carboxylic acid, we need to act with an acid. Yeah, just aqueous acid. That should make your nitrile group turn to carboxylic acid. Yeah. So again, we're just doing substitution. So I'm just gonna say H plus. Yeah. And what you'll see here is we're gonna go H3C. Again, literally following kind of the same principles that we had. And then we're going to substitute. So this becomes COOH. Yeah? Perfect. And then what else do we have to do? If we're going from a nitrile to an amine, what you need to know is we're going to do hydrogen with a nickel catalyst. So pretty much the same as hydrogenation of alkene. Yeah? Basically, we're going to do the same thing. But, again, importantly, you need to make sure that it has 3 carbons. A lot of people mistake and put 2 carbons. You need to make sure it still has the 3. So, like I say, you're following the same skeleton. So all of our compounds have had that. And then where the nitro group was, now you're saying, okay, there's going to be carbon, right? It's going to have 2 hydrogens. And then you're also going to have an amine group. Yeah? So, unfortunately, it does come to memorization. But even if you know the reactions, you just need to make sure, okay, let's look at the functional group specifically and just make the changes that we need to do. Okay, so this is a very interesting 6 marker, where we're talking specifically about addition reactions. Now, in terms of what we're doing here, we just need to get down the basics. We know it's a 6 marker, and we know they want reagents and reaction conditions, so we're going to give them all they want. Let's start with the alkenes. Yeah, we'll start with the alkenes, give them everything they want. So, in terms of reaction, I'm thinking, okay, what can I do that will have reagents and reaction conditions? Well, in my head, I was kind of thinking about doing like with HBr, because I know I can do reaction mechanism, but there's not really a specific reagent for that. So what I would maybe mention is about like alkenes react with hydrogen and nickel catalyst. I'd maybe just mention that, for example, just to kind of put it in. But really, what I would want to do is start with a reaction mechanism. I think maybe that's a bit cheeky to try and get a mark, but yeah, cool. The best thing I can think of is to do an addition reaction like that. So we're going to start saying electrophilic addition. That's the first thing I want to say. So always state what mechanism you're going to draw. So you're going to draw electrophilic addition. Now, what we'll do is we're actually going to use propane or propene, and we're going to do that for a specific reason, so that we can gain more marks, because we really want to impress the examiner. So, in terms of that, I'm going to draw propene. So C, let's do bond C, C, and then we can draw our hydrogens in like so. And then we need to remember, okay, where are we going to do this reaction mechanism? So, say we're doing HBr. Let's do H, BR. Now, we know there's going to be a dipole on this because bromine is more electronegative. So this is delta minus, this is delta plus. Yeah? And we know that negative charges in the double bond are going to be drawn to the hydrogen. Yeah? That arrow's maybe not curly enough, by the way, just so you know. Then we're also going to have to eject from there. So making sure the arrows are double-headed. That's the first step we want to do. Now, you'll see why we use propane. So we can say this, bang, bosh, bosh. If we put the hydrogen on here, I'm going to put the carbon cutter in here, keep the hydrogen here, bam, bam, bam. And then remember, we got the Br minus now. So from the negative charge, I'm going to go curly to the plus. And if we do that, what we can say is that is a complete reaction mechanism for the formation, for an addition reaction involving an alkene. Now, I use propene because I would maybe just mention about Markovnikov's principle. So maybe try and relate to like minor / major products just as an additional point afterwards. But the mechanism is the most important thing. Now, the next thing that you need to do is focus on the carbonyl compounds. So carbonyls. And again, we're going to do a pretty similar thing. So always name the reaction mechanism we're going to do. It's going to be nucleophilic addition this time. And again, we're going to draw the thing that we're trying to do. So I'm going to use an aldehyde just because I find it easier. But we're going to do H3C, bang, C double bond O, H. So we've got an aldehyde here. Now, again, think about the polarities. This is delta minus, this is delta plus. Yeah? Cool. So when you have a cyanide, like that, from the electrons, we're going to go to the carbon, which means we're going to put this on there. So that's a really badly drawn oxygen. Then we're just going to continue the molecule along. So make sure that you're really intentional with where those curly arrows are going. So we're going to do that. So you can see electrons under negative charge. You can see the hydrogen is now here, and the cyanide is going to be added on here. Cool. Now what you need to do as well is say, okay, there's a H plus here. Yeah, because we had acidified. Yeah, acidified conditions, right, with the sodium cyanide. Carry arrow to there, from the electrons to there, and then that's going to form your hydroxynitrile, like so. And then again, remembering extra details, I'd maybe mention about like sodium cyanide and like acidic conditions as well, just because that will kind of help you with doing that. So yeah, always make sure that you're mentioning things such as that, because it can help you to get more marks. But really, with this one, I think if you do the reaction mechanisms well enough, you're literally pretty much already getting 5 marks, to be honest, or definitely at least 4 marks if you've done both of those reaction mechanisms. And additional points can move you up, like saying the type of reaction mechanism you're doing, that can move you up into the 5 or 6 bracket. Okay, this is probably my favorite question in A-level chemistry, to be honest. It's a bit funny, but literally, you can get this mark so easily. So, first of all, make sure you draw the right thing. So, I hate that it's coming up. Okay, so drawing the right thing, and then make sure you really elongate this bond. Yeah? Cool. Why are we doing that? Well, because we're going to add dipoles. So we're just looking at the hydrogen because we know we're going to form a hydrogen bond. Yeah? We should know that when we see the question. Anything about dissolving in water, hydrogen bonding. Cool. So delta plus is going to go here, right? You can also put delta minus here. And if you really want to sell it, draw your electrons there. Cool. Now, what you also need to do is draw a water molecule nearby. So I'm going to do this. I'm going to make sure I've got my electrons there, my delta minus. And then we're going to go up here, delta plus, and we're going to go up here, or down here, sorry, delta plus. Then what you just need to do is you need to make sure that we do this going to one of the electrons. Cool. Or one of the pairs of electrons. And then let's just put the arrow here, hydrogen bond. And that will get you all of the marks. Literally, that will get you both of your marks. So make sure you're doing that. Now, in terms of naming esters, this is important. So we need to first of all look at the alcohol group side of it. So this is the alcohol group side. So we're looking 1, 2. So this is ethyl. And then we're thinking, okay, how many carbons are here? So 1, 2, 3, 4, 5. So we've got 5 carbons in the chain, and we've got this methyl group here. So in terms of where that methyl group is, well, this has to be carbon 1, 2, 3, 4, and 5. So it's on carbon 4. So we're going to call it ethyl because of the alcohol group. And then we're going to call it 4-methyl pentanoate, because that's how you name esters. So yeah, that's how we do that. Okay, so in terms of this reaction forming the ester that we saw in the last question, you just need to know about how we get from the carboxylic acid to the acyl chloride, and then we'll be able to get to the ester. So what you'll need to know is we need to use this molecule, thionyl chloride, so SOCl2, thionyl chloride. Yeah. So we're literally going to draw out what we had. So I think if you've seen it in the thing, literally just kind of repeat it. But we know this would have had to be a carboxylic acid, as I said in the question. If we react it with the thionyl chloride, what you should get is an acyl chloride. So it will look like this, but it will be Cl. And what you'll have is you'll have sulfur dioxide, and you also have hydrochloric acid. Yeah, that's a reaction that you'll just need to memorize pretty much, unfortunately. And then after you've got the acyl chloride, like we said in step 2, what you're going to do with that is you're going to react that acyl chloride with the alcohol that helps us from the ester. So we had ethanol. Yeah, so we're literally just going to react it with ethanol. And when we react it with ethanol, we're going to very happily form what we had. So you're just literally copying it pretty much. And then, yeah, you're pretty much just copying it. And then just remember, well, this H is now gone, that Cl is now gone. So they're just going to form HCl. And that should be that. Then when you're looking at the repeat unit of a polyester, what you really need to do is find the bond. So if we find the bond, this is the bond joining it together, that amide bond. And what we need to do is just split it up. So you know they repeat. So we got this one, and you got to think, okay, this surely came from a carboxylic acid. Drawing that benzene, I've done that really badly, but drawing the benzene, and then draw on the other side as well same thing. Cool. And then you just need to think, okay, the other molecule, what else was here? Well, this would have had to be the alcohol. Bam, bush, bush, bash, bash, bam. And that should be your answers. Okay, so this is a big question, and we've got alkaline hydrolysis. So just remember it's alkaline hydrolysis, right? So we need to kind of know what we're going to form and what bonds we're going to break. So let's quickly highlight them now. So I can see this is an ester bond, this is going to go. This is an amide bond, this is going to go. And again, we just need to think what we're actually going to form here. So when we break the ester bond, we'll form an alcohol and a carboxylate salt. Yeah, alcohol and carboxylate salt. Remember, it's not an acid hydrolysis, so we don't form a carboxylic acid, we form a carboxylate salt. Cool. Similar thing here, when we break off the amide bond, we're going to form, obviously, the amine, but then we're going to form a salt. Yeah, cool. So let's quickly work it. Let's look at the first bit first. So let's go to the left. Are we happy? We break it off. We are literally just going to get methanol. Yeah, so I'm just going to do CH3OH. Or do you know what? Let's keep it all skeletal. So we'll just do that. Fine. Okay. Now we need to think. Okay, what are we gonna actually have there? We're gonna have O minus, yeah, and we're gonna have the double bond O. Cool. Because it's on the carboxylate salt. Now let's join it to the rest of the molecule. So we can have this. We should all be happy with that. Now, one thing here. Okay, we have the nitrogen. Remember, always remember, we want to do NH2 now because it's amine. But if it was acid hydrolysis, we would have done NH3 plus if it was acid hydrolysis, but it is not. So we'll leave it at NH2. Then what else do we have? Okay, so we still have this double bond O, but then remember we said we're forming a salt, right? So O minus, yeah? If you put the Na next to it, I think that would also be completely fine. Yeah, if you put Na next to it. But I'll just leave it at that. So for some reason, I didn't even maximize the space we had. But I hope you're realizing we're looking specifically at the bonds, yeah? Look closely at the bonds and then use your prior knowledge to kind of paint the picture that they want. Okay, so we need to know about this halogen carrier stuff whenever we're talking about aromatic compounds, yeah? So make sure you revise that really, really well. Now, let's go to answering the question. So when we talk about electrophile, literally what we're saying is electron pair acceptor. So electron pair acceptor. Now, I always think phile just means to be attracted to. So electrophile attracted to electrons. So hence you must be accepting the electrons, yeah? That's why I go with that. Now, when you talk about outline the mechanism for this reaction, including the role of AlCO3 as a halogen carrier. Now, this bit, first of all, make sure you do this. So this one is it's pretty much an equation that you can memorize. So just look at what you've been told is being used, yeah? And you're literally going to follow the same steps. So AlCO3 plus, and then go for the compound that they gave you, CH3, CH2Cl. And then what you just need to know is this chlorine is going to bounce onto the aluminium chloride. Yeah, it's just going to bounce onto that. Yeah. So because of that, what we're going to have is we're going to leave this as just a positive species, that ethyl. Yeah. And then the AlCl is now going to be 4. It's going to be minus as well. So that chloride is just gone. Now, mechanism time. So I always like to name the mechanism as the first point of call. So I'm going to say electrophilic substitution is what's going on when we're doing with benzene. So let's draw the benzene ring because we're just forming ethyl benzene. So let's draw the benzene ring. Bam, 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 bam. And then draw that. Now, we have the ethyl group, right? CH2, CH3. And I've just done it that way so I can put the plus nearer. And then you need to go from the ring, curly arrow, to the plus. Yeah? Cool. So that's the first curly arrow that we have. Now, what we're going to do is actually now break apart the delocalized ring in benzene. So if you go here, draw a benzene, but now you're drawing it with the delocalized ring apart. So you have that. We're going to put a plus in the middle, yeah, because we've lost electrons. And what we're going to see is we have, bang, CH2, CH3, but we also have that hydrogen that was there that we're now just going to draw. Now, what we need to think about, okay, there's electrons in this one, and the ethyl group's kind of bully it. Yeah, it's gonna bully out the hydrogen. So this bond is going to break. so that the electron in there can now go back to stabilize the ring. Yeah? So we've had that, and now we're going to draw a final product, which is ethyl benzene. So CH2, CH3. So I forgot the ring because now we formed. And then that hydrogen just doesn't go into thin air. It's back. Yeah? And now, hydrogen back is an important thing. So at the end, we need to now regenerate the catalyst. We need to regenerate the catalyst. So because catalysts, we know, are not changed by the reaction. That's a very textbook definition of a catalyst. So to make sure that we know that hasn't happened, we're going to go back here with the proton, add it on to this thing that we formed. And then what you'll realize, okay, we should be able to form this guy again that we had in the start. And then also just using what we got left, HCl. So I hope that all makes sense. But that's your reaction mechanism. Okay, so now we have the case of directing groups. Back in my day, I thought you had to memorize this, but they've given it to you, which is good. So just look at here, okay, the cyanide is a free directing group. Yeah, so if it's a free directing group, then we should be happy in a mono-substituted compound, like it says in the question, that we are just going to direct it to carbon 1, 2, 3 here. So this is why the chlorine is now going to add on. Yeah, cool. Now, the next one, and by the way, I know this because it's a 3-mark question, so they're going to want you to draw 3 things. Yeah. So you look here, that was one of the 2, 4 directing groups. So I'm assuming one of the chlorines is going to go on carbon 2, and the other one is going to go on carbon 4. So that's why I've drawn it a bit smaller here. So we have the NHCO, CH3. One of them is going to go here to carbon 2, and then the other one, we're going to draw a different benzene, again with the NHCO, CH3, let's make sure that connects. It's going to now go to carbon 4. And that's how you're going to get your marks there. Okay, so it says that the reactions of phenylamine is similar to the reactions of phenol. Cool. So it wants to try substitution. So we're thinking, okay, this is a 2,4 directing group, amine, right? So we're going to draw a benzene, bish, bash, bosh, like that, and then you have the NH2. And then, if it's a tri-substitution, we're going to need 3 chlorides, yeah? And then, this is just a case of kind of knowing the reaction pretty much. But what you'll realize is we've got this, we've still got your NH2, and then the logical place to put it is 2, 4, and 6. And then you have 3 HCl, don't forget about those guys. Cool. Now, why does chlorine react much more readily with phenylamine than with benzene? Well, this is a very similar explanation to phenol, which you should know. So in terms of phenol, and the same thing with phenylamine, is that our major group, the oxygen or the nitrogen, has a lone pair. So lone pair on nitrogen is donated into the delocalizing. So donated into the, we can call it a pi system or delocalizing, whatever you want to say. So because it's donated to the pi system, what happens? Well, we have a higher concentration of electrons. Yeah. So if we have a higher concentration of electrons, what you want to say is key terminology, electron density. So electron density is going to increase. And because electron density is greater, we're thinking, okay, remember in electrophilic addition, the electrons from the delocalized pi ring want to attack the electrophile. Yeah? Does that make sense? Or it wants to attract the electrophile more. So that's what we're going to say. So if we have an increased electron density, then that means that we're going to attract the electrophile more strongly. More strongly. And that should be how you want to go about answering that question. Okay, so we're talking about alpha amino acids, and we want to find the molar mass of a polymer. Cool. So thankfully, they told us that the molar mass of the R group, so I actually am not really concerned about finding what the R group is at this moment in time. But what we do need to think, what is the total molar mass of one of the repeat units, right? So with this 91, I'm just going to add it into, okay, what else do we have here? Well, we've got the carbon and the hydrogen, so that's 12 and 1, so 13. We've got the amine group, which is, top of my head, 16. And then we've got the carboxyl group, which, top of my head again, I think it's 45. So if you add all of those together, you get 165. as your MR for the repeat unit. Cool. So if the amino acid of the repeat unit is 165, we're thinking, okay, there's 500 of them. So we can do 165 times 500. And that should get us, if we pop it into the calculator, 82500. Cool. Now, that's all well and dandy, but I'm already thinking 3 marks. I don't want to just put this down here and miss something. Yeah? So I'm just thinking as well, okay, well, whenever we do a reaction or whenever we're forming polymers, right, especially these type of polymers, you are going to form the amide bond, which means you're going to lose oxygen. Cool. So if we're going to lose oxygen, we're thinking, okay, if there's 500 molecules, how many amide bonds are there? There's going to be 499. Yeah. So we need to do 499 multiplied by 18. So 499 times 18 is 8982. So we'll do the 82500 minus 8982. And that should give us our answer, which is 73518 grams per mole. Okay, immediately with this question, I'm going to say take time because I'm struggling to draw this molecule too. So, addition polymers, you're looking at alkene groups. And condensation polymers, you're looking to form like amide links. Now, I like to follow the molecules really carefully and also just simplify whenever I can because it will make my life so much easier. So, if we start with the addition polymer, we have C bonding to C. And you can see with this carbon, we just have 2 hydrogens. So we're looking at the one furthest left. And in this one, we've got this on top, and we have all of this on the bottom. Yeah. So in terms of on the bottom, what I'm gonna really try to do is just make it as simple as possible. So if we have this carbon with a hydrogen, I can just see back here H2N, and I can see here COOH. Yeah, fine. And then we're just gonna repeat that again. So that's completely fine to draw. It doesn't look pretty, I'll tell you that much. Definitely doesn't look pretty, but we just need to focus on getting things in the right places to get the marks. And then don't forget your end bonds as well. Cool. Now, with the condensation polymer, this is a bit more difficult to draw. So we're thinking, okay, we need to join the amino acids together. Yeah, or the parts of the amino acid together. Now, what I'm going to do is just make my life really easy. So in terms of the amide link, we've got that. Cool. C. Now, this carbon, the middle carbon, that R group, I'm just going to simplify it all down. So I've got 2 carbons, 3 hydrogens. I'm just going to call it C2H3. Yep. And then we know that we've got a hydrogen down here. And then we're bonding it to what would have been the carboxylic acid group. But because we have the amide, we draw like this. And then now we've drawn one of the repeat units. Now we can do the second. So we're just going to repeat what we did. Bam. C2H3. And then C double bond O. Now, okay. We've drawn 2 repeat units, end bonds, gets you your marks. Okay, big question here. So a lot of context that we kind of don't need, to be honest, but I'm looking at the molecules that we have, compound G, it's compound H. So I can see really the biggest difference is the esterification of it. Cool. So we want to get a sample of compound H, and they've done it by refluxing G with methanol. There we go. And then they added an excess of aqueous sodium carbonate, and they purified H. Cool. Now, why does this use reflux in step 1? So whenever you're doing reflux, it's literally just the same thing. It prevents heat loss by evaporation. It prevents heat loss by evaporation. I think it's kind of like a buzz term that you should just say in exam whenever they want you to justify using reflux. Cool. Let's move on. So they said sodium carbonate removes the sulfuric acid catalyst and any unreacted compound G. So we need to think, okay, in terms of writing equation for the removal of sulfuric acid, I'm thinking, okay, well, sodium carbonate plus sulfuric acid, that's an equation I should know how to do. So sodium carbonate, thankfully, I don't think we need to use state symbols, they already mentioned, plus sulfuric acid. We're thinking we're forming salts plus carbon dioxide plus water because we're reacting with a carbonate. So that's what we're going to do. So sodium 2SO4 plus carbon dioxide plus water. And I'm just going to do a quick double check to make sure that everything is balanced, which it seems to be. So I'm fine. And then if we're saying about reaction here, I'm thinking, okay, well, what it's probably going to react with this carbonate, because well, what you would say about carbonates is that they're not really strong bases, right? So it's most likely going to react with the carboxylic acid group, right? So if we just go here, just add on the Na2CO3, oh my goodness, CO3, then we need to get to drawing. So I'm just doing this, and then we just need to get this in, and then, like we said, it's going to react with this, so we're actually going to deposit our sodium onto here, ONA, and then just think about it as well. The same kind of principle that we have plus CO2 plus H2O. Only thing now is that you can see here, well, we had 2 sodiums in the reactant, so we must have 2 in the products. So I'm thinking we need to add the 2 here, probably a 2 there, and then I think that will be balanced after that. So that's fine. If we go into the next part, sorry, it's just a really long question. In terms of another student says, maybe you could use sodium hydroxide, right? Cool. Now, sodium hydroxide is a bit of a stronger base, right? In terms of what's going to happen if you do it with compound H, well, I can see 2 issues, right? This is a phenol group that will react with the sodium hydroxide because phenol can act as an acid. And also, in like really hot temperatures, it can also be used for alkaline hydrolysis, right? So alkaline hydrolysis would break the ester bond. So that's kind of 2 things that we're thinking. Okay, I'm going to write down that NaOH hydrolyzes the ester. But I think it would also react with the phenol. So that's another thing that you can say. And then now we've got calculated percentage yield of compound H. So first of all, let's quickly see what the actual yield is. The yield is 5.32. And what we're going to need to do is, okay, compound G, I can find the molar mass of compound G, fine. When I have that, I can then find what the expected or the theoretical yield is of compound H. So that's what we're going to do. So in terms of theoretical yield, what we need to do is compound G, if we're using 8.97, so 8.97, we're going to divide it by its MR. So in terms of the MR, what I can think, okay, so we've got a benzene ring, which is going to be 12 carbons, so 12 times 6, plus, it's not substituted in 2 positions, so plus 4. So I've already got 76. Let's now add on the phenol group. So add a cheeky 17. And then after we've added the 17, I'm going to add the carboxyl group, which I know is 45 off the top of my head. So that means it's 138. So yeah, because I've done this a lot, I kind of remember some groups what their MRs is. But you can just calculate it as well with yourself by adding up how many like of each atom it is. But it's going to be 0.065 moles. Yeah. Now we see it's a 1-to-1 ratio. So in that case, what we're now going to say is we're going to use the 0.065 moles. Cool. So in terms of what the theoretical yield of compound H is, we now need to work out its MR. Yeah. There's probably another way we can do it, actually, to be fair. But yeah, let's work out its MR. Okay. So its MR is going to be, if I look at it, again, we're going to do the 12 times 6 plus 4, and then we'll add the 17 for the phenol. And then for this one, we're going to add the 32 for the oxygens. I can see 2 carbons there, so I'm going to add 24. And then there's going to be 3, so I'm going to add a 3. So it's 152. So 152 multiplied by 0.065 is going to be 9.88 grams. And that's the theoretical yield of compound H. Cool. So now we can do the actual yield, 5.32, divided by the theoretical yield, 9.88, multiplied by 100, and that should give us an answer. So if we do 5.32 divided by this times 100, then we've got 53.846%. It says 3 significant figures in the question, so we're going to do 53.8%. Finally, how do you purify impure compound H from the 2 layers in step 2? So just looking at step 2, so yeah, 2 layers are obtained. Now, what we really need to know is just what's going on here. So we've got 2 liquids, and the way that we're going to separate them is redistillation. That's just something that you need to know. Cool. So in terms of what we're happening, or the kind of method, we need a separating funnel. So separating funnel. And then you need to identify, is our organic layer going to be on the top or the bottom? That's what we want. So I'm looking here, its density is greater than water. Water is 1. So because density is greater than water, we're also going to mention is obtain the bottom layer. So with the separating funnel, you're going to let off the top, and you actually kind of it comes from the bottom anyway. So the bottom layer is what we want. Yeah. After we've got the layer, we need to dry with an anhydrous salts. Bonus if you can say examples, but I think saying an anhydrous salt is probably good enough. So like for example, you can say like calcium chloride, magnesium, sulfate, whatever. Cool. Then what we're going to say after that is we need to now re-distill to make sure that we got the pure compound. Its boiling point is 222. So I'm going to mention that. So redistill at 222 degrees Celsius. And then if we redistill it there, then we're making sure we only got the pure compound H. So that is how we answer all of those parts of the question. Okay, this is literally about as hard as it gets for an A-level chemistry question. So we are going to go through every single step of it. Cool. So we'll start with elemental analysis. So I might try and guess a way of doing it on here. But literally, you need CHO ratio. So use the ratio of all the compounds. 80.6, 7.46, 11.94. And what you need to do is you need to divide it by the MR. So 12, 1, and 16. Cool. So when we do that, rounding 6.72, 7.46, and then 0.746. And what you need to do is then you need to divide it by the lowest value. So we're going to divide all of those numbers by 0.746. So we'll get 1 to 10 to 9. Yeah. So that's how you do the elemental analysis part. Yeah. Cool. So percentages, divide by MR, then divide by the smallest. Yeah. That will give you your empirical formula. So that's the first one we write. So empirical formula. We're going to use the ratio. So from C, H, and O, it was 9 is to 10 is to 1. So the empirical formula is C9H10O. Cool. Happy days. Now, let's look at our mass spec. So in our mass spec, we need to look at, okay, what is the molecular ion peak? Yeah, the furthest one here. So again, we need to be a bit careful. I'd say you can tell, okay, there's 25 between here. I think each of them counts for 1. So 1, 2, 3, 4, 5. That's 130. 1, 2, 3, 4. So it's 134. So the molecular ion peak is 134. Yeah. So if we say Mz equals 134, then I can say that the MR of our compound is 134 grams per mole. Yeah. Cool. So now we need to use the empirical formula to link that in. Yeah. So what I'm saying is if we do 12 multiplied by 9 plus 10 plus 16, we get 134 anyway. So that means that 134 divided by 134 is equal to 1. So that means our molecular formula is C9H10O. Okay, that really helps us out because now we can get a better idea of what we want to work with. That's the molecular formula. So let's again now look at the infrared. So when I'm looking at the infrared, I'm looking, okay, get my data sheet out. Which peaks look a bit suspicious? So sorry, I'm just orientating data sheet properly. So when I'm looking at the data sheet, I'm looking, okay, there's this peak here. It's not too broad per se, but it's around the 3000s. Yeah, like high 2080s to low 2000s. And I'm just thinking, okay, that seems to me very, very much like it could technically be kind of nothing, to be fair. I don't know. It doesn't really look too much like anything. And there's nothing that's really in that region that I would think it is. So if I'm being honest, I know I've started to say that I don't really think that's going to be anything major. I think at best this might be like CH. So I would kind of mention this, but I think that's probably CH, to be honest, because it's not broad enough to be like a carboxylic acid peak. That's all. It's not far long enough to be an amine, which we don't have, and also it's not far enough to be alcohol. So I'm saying that's probably a CH peak. So let's look at what else we have. We have this guy here. So let's look at what this guy here could be. Well, we're in the region like 1,700. So I'm going to look 1,700. You can see, okay, there's an alkene there, but also there's a C double bond O. And we know we have one oxygen. So I'm saying probably C double bond O. Yeah. So that's what I'm kind of thinking at the moment. and I'd need to write down that thought on the paper. So we have a peak around 1,700. So we're going to say IR and a peak around like 1,700 centimeter to -1, likely C double bond O. Now, that's really useful information, because now what I can say is I think definitely we've got an aldehyde or a ketone, and that would help us out massively. And then also, I'm just going to quickly double check the IR again. To be honest, I saw this peak as well. So that peak as well is probably something we need to consider. So if we just look at the, honestly, because we're looking like 1,600 per se, I think that's probably going to be an alkene group. So we're looking at all of the things. So I'm going to say as well that the IR peak, we said it was around 1,600 centimeter -1, is likely to be C double bond C. Cool. So I'm thinking that that means that we have an alkene as well. And I think that would probably fit with our molecular formula. Yeah, it would. Okay. Now, what we now need to do is probably have a look at our proton NMR. So this is the fun bit. But looking at the proton NMR, again, just getting my data sheet the right way around. So let's just discuss all of the peaks. So I like to kind of start furthest left and work my way. So we've got a peak that's around 9. I'd say that's just around 9. I think that's fair enough. So if we say that we've got like 9.0 particles per million, yeah, I'm thinking, okay, first of all, let's get down. That's a doublet. So doublet integration 1. So doublet 1. And you're also thinking, okay, from the data sheet, what could that be? Well, to be honest, around 9, it's almost definitely going to be the aldehyde group. Like, I don't see how that can't be an aldehyde group. So, bang. I'm happy with that. So that's an aldehyde group. So that sorts one of our issues out. Now, what else do we have here? Well, I'm looking, okay. Let's look here. This is like, let's say like 7.3, 7.2, something like that. So like 7.3, let's say, particles per million. It was a singlet with an integration of 5. So we've got singlet with a 5. So when we have a singlet with a 5, I'm just thinking, what could that possibly be? So let's have a look on our data sheet. Singlet with a 5. I think, oh, sorry, 7.3, my bad. That's going to be, that's almost definitely going to be benzene. So this is molecules heating up. So this is a benzene. Okay, interesting. And there's 5 of them, which is very interesting. So that means that we've got a substitution in the benzene ring. Okay. Now what I'm looking at is the next peak. So we had, oh, cheeky, 1, 2, 3, 4, 5. So that's actually a quintet, I believe it's called. So we have a quintet around 3.9. So let's say, let's go some space, 3.9 ppm. It's a quintet, and it's integration of 1. So I'm just thinking, okay, 3.9, what could that probably be? So just thinking of what we have, 3.9 is probably likely, oh, goodness gracious me, HCO maybe? But I don't think that's likely, to be honest. I'm a bit confused by that one, to be honest. I'll probably leave that. I'll probably leave that for now. For now, we'll leave it, because I'm not too sure what that could be. And then finally, if we look at the 1.3 here, that's a doublet integration 3. So we've got like about 1.3 ppm. It's a doublet. Its integration is 3. So because we've got that, I'm thinking, okay, if it's integration 3 and it's a 1.3, it's definitely HCR, and that's probably going to be a CH3 group. So HCR, and we think it's probably a CH3 group. So now we just kind of need to put things together. So I think the most obvious thing to start with is the benzene ring. Yeah, I think that's probably the best thing to start with. So let's just draw a benzene ring. So drawing a benzene ring, and we know that it's only going to be substituted in one place because it was an integration of 5. So I'm happy. I've used that information. Now I'm just thinking, I think this quintet was likely just because of I don't really know what it was, but it's got to be a carbon. Oh, no, it's got to be a hydrogen next to 4, yeah, because of its integration. So that's interesting as well. What we also know is this aldehyde group is always going to be at the end of a chain, and it's a doublet. So that means it's attached to a carbon with 1, yeah. So I'm just thinking as well, if I just draw a different part of a molecule before we put it together, this is attached to a carbon with 1, yeah. So that's also very interesting information. And then, if it's 1, then that must have been... Oh, sorry. And we also had a CH3 group. Yeah, because we have a CH3 group. So it's a doublet, which means it's attached to a carbon of 1. Yes, that's true. And it's a doublet. So this one, CH3 group might be here. Because then that would be attached to a carbon with 1. So I'm thinking that's pretty likely. And then when I put that all together, you can see I've got 1, 2, 3 added to the 6 that we had. So we've already got 9 carbons. So if we just put that together, that should actually be our molecule. So I'm going to just rub that out. I'm going to draw it underneath because it will look better. But if you go like this, bam, bam, and then C, we said it's H, CH3, and then C, double bond O, H. I think that will be our molecule. Yeah. So just to double check, just do your checks. We've got 1 oxygen. How many carbons do we have? 1, 2, 3, plus the 6. We've got 9 carbons. And then the hydrogen was 10. So thinking 1 plus 3, 4, 5. And then added to the 5 that 10. So I'm very happy. I think that's our molecule. So I hope the kind of rationale I've went through, and I didn't necessarily know all the bits and bobs, but you can see we can make the molecule based off that. And I would be happy to put that down as my final answer. Okay, so that is a wrap on the past paper. I hope it was really, really helpful in terms of understanding the kind of technique to answer some questions, or maybe some nuances in terms of thinking about your approach towards these questions. So hopefully it's helped. I know organic chemistry is a very, very difficult one. So just make sure you're practicing and preparing yourself really well for that exam coming up. Any questions at all, drop them in the comments below. If you liked the video, please like and subscribe to the channel. We've also got a TikTok and our Instagram, both at demola. Links should be in the description below. But that's all for me from now. So thank you so much for listening. Best of luck with your exams if you've got them coming up soon. And we'll catch you in the next one. Bye for now.